AguaClara LLC. I'm here today with Chuck Brown, Director of Planning and Development, sitting in the front row. So I'll talk to you a little bit about how this company got started. So what is AguaClara? We design water treatment technologies that are electricity free, so we can install them in rural villages. We work with in-country partners to build these designs, and then we help that partner train the communities to own and maintain the systems on their own after we leave. Why is this important? Well, 1 billion people around the world don't have access to clean drinking water. 2 million people die from waterborne disease every year, and most of those people are children under 5. So the person who started AguaClara as an academic program was Dr. Monroe Weber-Shirk. He worked with Salvadoran refugees in Honduras, right here in Mesa Grande, as you can see, in the early 80s. So he witnessed people having to walk very far to public taps, stand in line, collect water, and bring them back to wherever they were staying. He came to understand the difficulties of having to go through that. So he was inspired to work on water, drinking water as a problem. So he came back to the US, he studied at Cornell University, studied slow sand filtration, got his PhD, became a professor. And then about 20 years later, he was invited to develop drinking water treatment systems for Honduran communities. So by the time he was invited, there was a lot of infrastructure development in Honduras. There was gravity-powered water supply, which looks something like this, where you have an uphill source of water, and that would be piped downhill, so just gravity is driving that force. So that's pumped downhill to a distribution tank, where the water will get chlorinated, and then again, by gravity, that water is flowing to a downhill community. So theoretically, all we have to do is take a water treatment plant behind our distribution tank, and our problem is solved. So if we look at what some of the existing solutions were, we had packaged plants, which are these prefabricated plants that you can kind of fly in and plop into a community and with very little assembly connect it all up. Or you would have a mechanized plant, which basically will end up looking the same, but you build it in place as a civil structure. So one of the problems with these packaged or mechanized plants is that they're full of pumps. So that makes it very expensive to run because of the electricity required. And the pumps are also really prone to breaking down and failing. These packaged plants are also really inconvenient to operate. As you can see, this ladder was built for the operator to climb and look into the tank, and it doesn't look safe at all. It's also really difficult to understand what's going on inside of these plants. Here you see a reactor. You don't know what's going on inside. If ever he has to open it up, how would he even crawl inside and see what's going on? It's really difficult to work with. The systems are fairly non-intuitive. It's complicated. This is a picture of the motherboard at one of our plants. And we're talking to the operator, and we asked him, there's a bunch of red lights on your circuit board. That can't be good. What does that mean? And he said, I don't know. So, not very helpful. Okay. So the problem with packaged and mechanized plants, the cost of electricity is prohibitive. A generator is required when the power goes out. How do you get specialized plants into such rural areas? Pumps, sensors, circuitry, prone to failure. They're not operator friendly, and they're difficult to troubleshoot. So based on that, we might say we should use a point-of-use system. So a point-of-use system is a kind of treatment system where you treat your water on the spot and drink it just as you're treating it. So for example, we have biosand filters, these concrete boxes filled with sand or other filtration media that are sometimes in people's homes. Or life straws. This straw, as you drink from it, it treats the water as the water flows through it. So point-of-use systems are fine for some places, but there are some problems. You're only treating the water you drink. So if you're washing your hands with water that's untreated, or you're washing your glass with water that's untreated and then you're putting clean water into it, you still have many ways of getting sick. Operation and maintenance is also dependent on your ability to train individual households. So if you're going into a village of about 500 people, every single one of those people needs to know how to clean their filtration media, when to clean it, how to handle it properly. If you're giving out life straws, how do they know when to replace them? It's a pretty big task. Oftentimes it's more expensive to use a point of view system than a community scale system, but that's not always true. So, but anyway, for hygiene and all the other reasons mentioned, we want to have access to drinking water via tap as much as possible. So how can we make a centralized system that works for a small community? We need to develop a fundamental understanding of the physical processes that govern water treatment, and that will allow us to innovate. Okay, that sounds obvious. Don't we already know the physical processes that govern water treatment? Civil engineers, how do we do this? Well, let's look at the design for something called a hydraulic flocculator. A flocculator is a piece of machinery that gently mixes your water so that all the dirt in the water will collide and form clumps called flocks. And those flocks will grow slowly larger and larger and larger until they can settle out of the water. So if you open up a textbook, you'll see some design recommendations that look like this. You have a velocity range, a depth of water that's mandated, and a distance between your baffles or plates that force your water to move in a certain way. So you have all these recommendations, and then they say your flow needs to be greater than 115 liters per second. Well, this is all a little fishy because we don't see any equations here. So what are these design guidelines even based on? We don't know why certain velocities work really well. And what happens when we want to build something for a small community where we only want to run 10 liters per second? These design guidelines fall apart. So when we are trying to figure out what these physical processes are, we also want to include new innovations that will make it sustainable in a rural area. So we want to talk about designing a system where operators with a 6th grade education can run the system. The plant can be made with locally available parts so that it can be repaired easily. The components need to be modular so you can swap things in and out really easily and clean things easily. The tank should be open so you can look inside and observe what's going on, troubleshoot things. We shouldn't require any electricity for the systems, and the system should be scalable from small to large communities. So at AguaClara, that's something we have managed to do. The tall guy, you can see, that's Mickey Edelman. He's an AguaClara alum. He's actually teaching elementary school students how one of our plants in Honduras works. And here you can see operators actually taking apart one of the tanks in our plant for maintenance. And so anything they're pulling out can easily be remade and replaced. Okay. Why has the private sector failed to optimize municipal water treatment? Well, vendors want to sell hardware and consultants want to minimize their liability. So consultants are always calling up vendors and saying, all right, give me a 100 liter per second plant, and if anything goes wrong with it, they can just blame the vendor. So you end up with hardware that isn't easily accessible in a rural community. So if anything breaks, you're in trouble. Also, vendor designs are proprietary, so they're just trying to mass manufacture something, and that helps them maximize profit. And they don't want to risk failure on a unit, so they're over-designing things, making it expensive. So when you design a plant, you're plopping it into a town, and you're running away within 2 or 3 months. You have no idea what the issues were with your system, and you just keep mass manufacturing the same problems over and over again. So if the private sector can't do this, we need an open source, university-based research and development model. So what we'll do is, in Cornell University, where Monroe had started this project, he runs the research lab where we try to figure out how does water treatment really work. We do the modeling, we do the computational fluid dynamics, and we come up with actual equations. That allows us to automate designs that we can then build in the field. And once we build the designs in the field, we sit with all the stakeholders, we sit with our partners, we sit with our operators, and we evaluate. And we say what worked well, what didn't work well, what were the problems. And then we take those problems back to the lab and we start over. So based on this model, the first iteration of our design looked something like this, where we're taking our raw water from a river source. We add a coagulant to make the dirt in the water sticky. Then we flocculate that water so that the dirt sticks together when they collide, when the dirt particles collide, grow larger and larger and larger. Then they enter the sedimentation process. So it enters the bottom of the tank, the water flows up, and that flock is now heavy enough that when it hits a plate, it falls down. And then you've got clean water coming off the top, which you'll chlorinate, and then becomes suitable for drinking. This is what the CAD of that looks like. Your square box is where we add coagulant. The large rectangular structure directly adjacent to that is our flocculator. The insides of that look like this. Those blue plates are baffles. And here they are stuck into the tank. Adjacent to the flocculator is the sedimentation tank, which inside looks something like this. Oops. Okay. So based on that, we built our first plant in the town of the municipality of Ojojona in Honduras. And so a bunch of students went in, worked with local people to that municipality, and started building this up. And as you can see, everything is just concrete, sand, pipe, plates, everything you can just very easily get locally. So that project began in January of 2006, came online about a year and a half later, and we were able to treat 80 NTU water down to 3 NTU. So NTU is a measurement of how cloudy or dirty the water is, and if you look, 80 NTU water, the higher NTU is muddier, and we were able to get it pretty clear. So that was a great first try. However, we did screw up quite a bit. This was a flocculator that eventually got torn down because it didn't work at all. We didn't know how to flocculate at such low flow rates. So, however, the students kept at it, and eventually different parts of that plant were repurposed to help us flocculate properly. And the design has come a long way since then, so now we have about 11 plants running in Honduras, serving over 50,000 people. They're a lot easier to run. Now we put things in buildings, so it's a lot more pleasant to operate the plant, especially if it's raining. You can see from our CAD, we've made a lot of changes to the design. Specifically, I want to talk about 3 things. We improved our sedimentation process, so it works much more effectively. We invented a rapid sand filter that requires about 1/6 as much water to backwash and 1/6 as much area as a traditional rapid sand filter. And we have a chemical dose controller that delivers an accurate chemical dose without sensors, pumps, or electronics. So first, the sedimentation tank. This was the first sedimentation tank we built in Ojojona, and we weren't getting the size of our flocks right. So they were settling out in the wrong place in the sedimentation tank too early, and so the operator would have to take apart the sedimentation tank and shovel out all that gunk. Not very fun. But eventually, we started to realize we can actually make sedimentation better and eliminate this maintenance problem if we violate something most engineering textbooks will tell you, and that is not to break your flocks. So one of the velocity requirements I showed you earlier, a lot of that comes with this idea that you are trying to grow the size of your dirt particles so that they settle out easily. But actually, if you break them up to a slightly smaller size, you can make a flock blanket. And the flock blanket looks something like this. If it'll let me. That's my mouse. There. So it's just a suspension of all that coagulated dirt that acts as a natural filter. And that'll sit at the bottom of the sedimentation tank, and it filters the water amazingly. And then any excess flocks spill over the side into a flock hopper. And then you just open up a valve and purge it all out so there's no shoveling involved anymore. So we can see how effective that process is. On the left you see the dirty water. On the right, I don't know if you can see that where you guys are sitting, but the water is perfectly clear. We also invented a new kind of filter, which takes the concept of your traditional rapid sand filter, which is usually 6 filters running side by side, and then when you want to clean one of them, you have to shut off flow to 5 and take all of that flow and reverse it through the 6th filter. So eventually we realized it'll be much easier if we just put all of those 6 layers of sand one on top of the other. So you save 1/6, you have 1/6 of the area you would normally require. And then when you backwash it, you're backwashing all 6 layers at once. So you're using 1/6 of the water you would otherwise. Also, we improved our chemical dosing. So we probably have the first system in the world that doesn't use any sensors but can actually automatically adjust chemical flow based on plant flow rate. So here's our original system. You can see that little bottle has a chlorine solution in it. If the operator decides he needs to dose a little more chlorine today, he'll pull out that tube from one of those holes and stick it into one of the lower holes, and that just increases the flow of the chemical. But it's, if the plant flow decreases, that chemical flow is still going to be the same. So this is what our new system looks like. The new system has flow linearizing tubes, which will be very important, and I'll explain why. And inside of the tank, there's a pipe sticking out right there that we call an elephant. And that linearizes the relationship between the height of water in the tank and the flow through the orifices in that pipe. So if we look at a schematic, inside of the tank there's a float. And that float is going up and down based on how much flow is going through the plant. So if the flow reduces 50%, the height of that float goes down by 50%. And your discharge point, I wish I had a pointer, I'm sorry, that discharge point will go up by 50%. So, you see that H? That H is measuring the height between your chemical fluid level and your discharge point. And that tells you how much energy you have for the flow of that chemical. So, if you want to add more energy, you want to increase the flow, the operator will slide that discharge point down like this. So now you have more energy. So when the water is a little dirtier, he'll add more chlorine. And then when the plant flow changes, that water level in the tank goes down and that energy, that height, also decreases. And when the plant turns off, your discharge point is at the same level as your starting fluid level, so there's no flow. Okay, so those are some of our major innovations. We have a pretty good design. There's always room for improvement, but we really want to start disseminating this technology. The technologies are open source, and the designs are available online. And in 2011, I started working in Monroe's lab after graduating from his program as a design engineer. And I was customizing those designs for partners who had been contacting us who were interested in the plans. However, these partners were not taking the plunge and starting projects. In Honduras, we were getting projects done because there were AguaClara alumni who were applying for Fulbright scholarships. And so when they would get that, they would go down to Honduras and help our partner. But that was very limited. That wasn't going to help us really expand. So what did we need to get new projects on the ground in new countries? And that's where AguaClara LLC came to be. We provided professional on-the-ground engineering services. So in 2013, we got our first opportunity as a company. The Tata Cornell Initiative approached us and asked us to build AguaClara plants in India. So that should be simple enough. We just need to find a village that satisfies our constraints, and we can just plop that plant right in there. Except that didn't work at all because the context was totally different. Unlike the gravity supply systems you see in Honduras, what we saw in most villages was our water source coming from a lower level than the villages. So you would have a lowland sanitary well and a diesel pump that would bring water from the well up to an overhead storage tank that was maybe 20 to 40 meters above the well. And then it would gravity feed down to a village of about 500 people. Also, if we look at the quality of that well, the well water is reasonably clean year-round. You're not going to get that brown, nasty water that you saw in Honduras. So we don't even need to flocculate or do sedimentation. So the solution we thought was to scale down our stacked rapid sand filters and then scale down our chemical dosers. So our original stacked rapid sand filter design was unfeasible to build on top of a tank, so we needed to make a more compact or closed version of that. So we started building it in a pipe, and you can see that's a half fabricated enclosed stacked rapid sand filter, E-Stars filter, in a 24-inch diameter pipe. And so our proposed system looked something like this. We had, since our diesel pump would run at about 15 liters per second, and we had a filter that was running at about 3.2 liters per second, we needed to add an extra overhead storage tank. So you would pump the water up fast, run the water through the filter slow, collect the water in your third storage tank, and then pump it again fast, or gravity flow it fast down to your village. It's pretty messy. So luckily, although maybe unluckily, because we'd already started constructing and fabricating, we found that there was a solar pump capable of pumping water about 20 or 40 meters. And we were talking to some people in the villages, and they were saying that diesel is really difficult to obtain, and the cost is really volatile. So if the price of diesel doubles in a year, those systems are done. They can't maintain it. So we decided it makes sense to change the system, and now we have to talk about handling fluctuating flows for the filter. So we decided, let's install 3 12-inch diameter filters that run at 0.8 liters per second. So if there isn't enough flow on a certain day, you can shut off 2 filters to backwash one of them. So here's the new system. It looks a lot cleaner, and just the final of what it looks like. We can eliminate the extra storage tank because the pump flow will never be greater than your combined filter flow. This is our lowland sanitary well. Our solar pump is submersible. It sits inside the well, and we have a house for the pump controls, and then the solar panels sit on top of that pump house. And we have our filters, 3 filters sitting up just above the overhead tank in a facility, our chemical dose controllers, and your gravity feed down to the villages. So we had to break some of our own rules when we did this. We designed a closed tank, and it's not easy to see what's going on inside. We also included a pump in the distribution system, and we always said pumps were a big no-no. So is it still sustainable? Well, some things that were lucky for us is that these community members are really used to working with pumps, and there are a lot of local pump technicians around. And we also found that the solar panels are also distributed locally, which is great news. And there are lots of government subsidies for our solar technologies. So the answer is we hope it's still sustainable, but we don't really know. We also had to modify the training since we're dealing with closed tanks. So when we brought the filters out to site, they were taken apart, and we had the operators put them together with their own hands and install and start up the technology with us. We also had to add some visual feedback to the system. So this is one of our school-aged operators. He's backwashing the filter. And there's a clear pipe connected to the filter. I don't know if you can see that. And so when he backwashes, that clear pipe is acting as a manometer, and he has an idea of where that water level is supposed to drop to. You see it drops down from the top. And that kind of tells him, is it backwashing properly? So that project wrapped up about a month and a half ago. And so far, as far as we know, things are still running well. We're keeping in touch with them. We hope it'll last. And so just, I wanted to leave you with some thoughts about how we can use engineering as a force for good. So it's really important that you do something that you're passionate about, and that'll keep you going through some of the worst challenges that you will face, and there will be many. Take the time to understand the problem and study existing solutions. Don't be afraid to defy what you've been taught, whether a professor has taught it to you or a textbook has taught it to you. Gather feedback from all stakeholders. When you're providing solutions to people, they will know your technology better than you will eventually. And they will give you better feedback than you can ever come up with on your own. So talk to them. And stay flexible, and don't be afraid to break your own rules. So that's it. Are there any questions? Yes?
So So for the first project in that first city, you said that you had to redo the flocculators.
Yes.
So I thought you guys had like tested it in the lab with a specific like scenario. Why did you have to redo it there?
Well, the things that we tested in the lab, we didn't test it at scale.
Okay.
So yes, we have lab setups and whatnot, but what happens when you actually build a full-scale plant? It's totally different, and it just didn't work out the same way. So, yeah, go
And
ahead.
can I also ask, like, how much does one plant cost to build, and how long?
So those Honduras plants, it's about $10 to $15 per person in a community. And that depends. A bigger plant will cost less per person, and a smaller plant will cost more. In India, it cost about I want to say $100,000 for the system. Yeah.
It's not bad. Like for the whole like building and materials and everything.
Everything.
Okay.
Yeah.
Well, first of all, thanks for the presentation. And like, how open or not were like the local people to like some foreigners arriving and saying, "Oh, we want to implement a solution that will get your clean water"? Like, do they perceive the water that they had as a problem? I mean, what were some difficulties you encountered in terms of community?
Yeah, so this is a really good question, and we know that we're coming in as outsiders, and so that's why it's so important that we work with a local organization. So I'll talk mostly about India because that's where I worked. We worked with an organization called Pradhan there, and so they had a long relationship with the communities they were working in. So they already had started sensitizing the community to the importance of clean water, and a lot of them were already aware of these issues and wanted clean water, but they were still important in terms of gaining trust in the community and just getting people to work with us and organizing the project to suit their needs. So definitely, if we hadn't worked with Pradhan, it would have been a real challenge. It's a whole different culture, there's different languages, sometimes there's multiple languages in a single village, so they were really instrumental in helping us in that way. Yeah.
Why did you guys decide to register as an LLC?
So, do you want to take this?
I mean, that made a lot of sense for us in terms of, we started as a small team, so you did it as a partnership, So we're really interested in this idea of being a social enterprise, right? As opposed to starting up as a nonprofit or continuing to just working, outside of the university. It gave us a lot of options, a lot of flexibility. I think it made us more agile. And also the sense of, so when you get involved in international development, you don't want to. One of the big things you go against is creating dependencies in some of the communities that you work in. And so, sometimes when you find that NGOs or nonprofits, they go in, if you take in kind of a handout approach as opposed to something more, a little bit collaborative. And we ask, like people are paying for the clean water and they pitch in and they provide support and construction, everything else. It creates more of a sense of ownership, and that's just kind of an approach that's very inherent in working in a social enterprise. So it made sense for us internally as starting as a really small team to be an LLC, but then also just the concept of taking the social entrepreneurial approach, be more collaborative, engaged, and really feel like we're creating value as opposed to just trying to transfer it. That's what made sense for us.
Can this product filter like ocean water?
No. So basically, our technologies will treat water for turbidity, which is that cloudy muddiness, and we don't treat heavy metals, and we don't treat salinity. The reason this is still widely applicable is because most surface water, so most of your river water, or even that lowland, the shallow well water, can be treated by it, and we really don't recommend using groundwater because groundwater will have the arsenic, the fluoride, which is pretty bad for your health. And treating that water means we need to figure out how to dispose of all of that dangerous byproduct, and we don't want to get into that with these people. So, yeah.
So usually, does the government subsidize most of the costs for implementing the system, or like how does?
Yeah. So in Honduras, basically the municipal governments put up a lot of the money. Communities will also put in a fraction of the money, whatever they can afford. There have been other outside donors like Rotary, Swiss, what is it?
Swiss Agency for Development and Cooperation.
Yeah, and so in India, there are private donors, but the government is putting up a lot of money, and they're basically putting in these systems for free. The communities are not putting in any money for these. Just the operation cost to maintain it in the long run. But the infrastructure, the government's putting in.
What was your favorite part about this whole design process?
Working with people, it was so exciting, and you know, we spent a lot of time working with the operators. They were kind of with us from the beginning of the project, and because it was a pilot, we really were learning together. And this is where you really see the benefit of having an open source technology, is when you're actually able to explain to people why things are designed the way they are. You can bounce ideas off of them, they can contribute, they can give you ideas. So you're learning the technology together, and it's so exciting to see how at the end of the project, when you start pulling out more and the operator is working more independently, they really do know more about your technology than you do, even if you designed it. And they can be telling you, you know, they get really comfortable just tinkering with the system, and it's really amazing to see. Yeah.
Is operator like a full-time position, or do they just have to go once a day?
So in Honduras, we would have 4 operators, 2 people working a day shift and 2 people working a night shift. Those plants run 24 hours a day. In India, the plants they only need to be operated for about an hour a day. So you would have 1 operator. So actually there are 2 operators, and they might alternate on days. Yeah.
Is there any sort of like long-term system put in place for like maintenance and follow-up? Like, is it up to the community to like come to you like 5 years down the road if things stop working as well, or is that kind of like?
Yeah, so the idea is that we train the local partner in the technical aspects as well. So if for some reason the operator is at a complete loss and they need outside help, first they would go to our local partner. If the local partner is also at a loss, then we're always here, and they can certainly come to us. But we hope that the operator is well trained enough, and like I said, the operator really does seem to know the system better than we do. Like when we're out of the village for a month at a time, we come back in, we forget how to run everything. So I would hope that it doesn't come